Have you ever had a hunch, a guess, that you just knew in your gut was right? Well, imagine it takes the rest of your life and then some to actually prove it. That's exactly the story we're diving into today. A mathematical guess that looked simple but took nearly a lifetime to solve.
It's a really fascinating question, right? In math, you can't just say something is true. You have to prove it, beyond any shadow of a doubt. But what happens when that proof is just incredibly hard to find?
And in this case, the answer is 69 years. Yeah, you heard that right. Not a typo. 69 years of work, spanning generations of mathematicians, all chasing one single stubborn problem.
All right, so let's set the scene. Our story kicks off over a century ago, with a conjecture that looked pretty straightforward on the surface, but was hiding these incredible depths of complexity.
So, in 1916, a German mathematician named Ludwig Bieberbach makes this very specific guess about a certain type of mathematical function. We're talking about functions that are super smooth, really well behaved. He actually managed to prove the first tiny part of his own guess. But the rest of it, well, the rest became one of the most famous unsolved problems in his field for the next 7 decades.
Okay, so to really get what he was guessing at, we kind of need to wrap our heads around the world he was working in. And trust me, this isn't just about crunching numbers. It's about shapes, transformations, and the actual geometry of these functions.
The field is called geometric function theory. And honestly, the best way to think about it is like, it's mathematical Play-Doh. Seriously, you start with a shape, and then you use a function to twist it, stretch it, or totally remold it into something new. The whole goal is to figure out the rules of this reshaping game.
And this visualizes a core concept here. It's called a conformal map. Imagine that grid is drawn on a sheet of rubber, and you start stretching it. With a conformal map, no matter how much you distort that sheet, everywhere the lines used to cross at a 90-degree angle, they still cross at a perfect 90-degree angle. The lengths might go crazy, but the angles stay the same. This is an absolutely crucial idea.
Okay, next key idea, a special type of function called univalent, or if you want to use the original German term, schlicht, which basically means simple. And a schlicht function, like the one on the left, is well behaved. It stretches a shape, sure, but it never folds it back onto itself. In contrast, look at the function on the right. It's messy. It creates overlaps and folds. Bieberbach was only interested in these nice, polite schlicht ones.
So this brings us right to Bieberbach's central question. He was looking at these schlicht functions. Now, he knew that any one of these functions could be described by an infinite series of terms, and each term has a number attached to it called a coefficient. His big question was surprisingly simple. If we know for a fact that a function is schlicht, is there a predictable limit on how big those coefficients can get? He had a hunch there was.
But proving that hunch, oh man, that turned into a mathematical marathon. This wasn't one person in a dusty attic, it was a global, multi-generational relay race. And this timeline really shows you what an incredible journey it was. So Bieberbach kicks it all off in 1916, proving his guess was true for just the second coefficient. 7 years later, in 1923, Charles Lohner comes up with his brilliant new method and proves it for the third. Then in 1936, M.S. Robertson doesn't solve the next step, but he proposes a related, stronger conjecture that ends up being a crucial piece of the puzzle. For decades, it was this slow, painstaking march forward.
A quote like this kind of hints at why mathematicians thought the problem was solvable in the first place. It's basically saying that the very property of being schlicht, of being well-behaved, is stable. It doesn't just break easily. And that stability gave researchers the little handholds they needed to keep chipping away at the problem over the decades.
So, decades passed, the problem became legendary. A lot of people believed it was probably true, but that a general proof for the whole thing was just out of reach. And then, the solution arrived.
I mean, just think about that. For 69 years, this was a white whale for mathematicians. Proving it, or even just proving it for the next coefficient in the series, was a major achievement that could absolutely make your career.
And the proof didn't come from one of the major centers of research that had been hammering away at it for years. Nope, it came from Louis de Branges, a mathematician at Purdue University, and his approach was so different that at first many people were pretty skeptical.
His strategy was just brilliant. He didn't charge straight at the main problem. Instead, he proved a related idea called the Milan conjecture. That proof automatically proved Robertson's conjecture from way back in 1936. And once Robertson's conjecture was proven, it was already known that Bieberbach's original guess from 1916 must also be true.
It was like a chain of dominoes that had been set up over 50 years, and de Branches was the one who finally tipped the first one over.
And here it is, the grand result of 69 years of work. And the rule governing those coefficients was breathtakingly simple. The absolute value of the nth coefficient is always less than or equal to n. That's it. So the second coefficient is less than or equal to 2, the third is less than or equal to 3, and so on, forever. Bieberbach had guessed it perfectly, all the way back in 1916.
So after 69 years, the mystery was solved. But you might be asking yourself, okay, cool story, but why should I care about the coefficients of some abstract function? Well, it turns out that the tools developed to hunt for this proof are surprisingly practical.
And this is the big question with a lot of pure mathematics, isn't it? Why does it matter? The answer is that this abstract study of how to map and reshape complex forms has found its way into some of the most advanced technology we use every single day.
And the applications are just stunning, because they all come down to accurately mapping complex shapes. This is fundamental to aerodynamics, predicting how air reshapes itself around a wing. It's used in engineering to model how a bridge bends under stress. And maybe most surprisingly, these principles are at the very heart of MRIs, which have to translate the complex shapes of our biology into clear digital images. Even the virtual worlds in video games rely on these very same techniques.
This quote really just sums it all up. What started as this abstract guess back in 1916 ended up creating essential tools for describing the physical world and building the technology we rely on today.
And that leaves us with a final, fascinating thought. The 70-year journey to prove the Bieberbach conjecture wasn't just about finding an answer. It was about developing a whole new language to describe our world. It really makes you wonder, what seemingly obscure problems are mathematicians working on right now that will become the foundation for technology we can't even imagine yet?